Welcome back everybody to the Bread and Burt YouTube channel. Today is an episode all about brake ducts, so if you don't like brake ducts, move on. Let's get to work. So if you think what we've done up until now is redneck, this is going to take the cake. So if you watched the last episode, you'd see that I was having a little bit of trouble getting a brake duct design to print that would work. But I found some new information. I was kind of thinking that James was going to limit the steering rack based on distance, and we needed to get the steering rack limiters on it so that I could see how much, he was wanting to limit. Turns out he was going to do it by rotations of the steering wheel, and that's something I can simulate right now. So what I've been doing is simulating 1 1/4 turn of the steering wheel. And I've got a brake duct design here that I think will work. It's on the car right now, so I'll pull it off in a second to show you guys what it actually looks like. But right now, this is just a PLA prototype. This thing would never last in this situation. It would melt immediately, but it's just a prototype. I put some tape on it to experiment with the gold heat tape I'm gonna use, just to kind of get a feel for it. So this is by no means a finished product. So I've got a jack under the suspension here to put the car at a little bit more than 1G state. This is a little, technically riding a little bit lower than it would be with the tires on and full weight on it, but it does simulate a corner. So this is about as high as I can jack this thing up without knocking it off the stands. And this is the duct that we have in here. So it is a 3-inch inlet as opposed to the old 2-inch all the way to the duct. It is a short run from what will essentially be right there to right there. They'll just have to make sure that we guide it correctly. We may have to tether it somewhere right here, but I'll address that with the next prototype. I may angle this just a little bit further that way to kind of force it away from the tire, force a little bit more of a bend into it. And I may actually angle this upwards a little bit. So then its cross-sectional surface area is somewhere like right here, here, here. It goes down from 4,400 millimeters squared here to like 2,700 millimeters squared here. And then it goes down by 200 in each section until it gets to the end here, which is 1,700 millimeters squared. So the airspeed going through this thing is gonna increase quite a bit. In a perfect world, it would be a linear change, but when you get pressure and flow restrictions involved, it doesn't end up that way. But yeah, it bolts on here and here, uses use of the factory ABS mounting holes. This knuckle does not have it, so I'll have to tap them. It also bolts to the knuckle right here. This flange needs angled back just a touch, but it's honestly close enough here that I think it would actually just pass. But yeah, that's it. So then what we'll do here is I'm gonna go full, well, what will be full lock 1 1/4 turn right. Let's take a look at that and see how that clearance looks. This looks like everything on the backside clears just fine. No concerns there. It looks like the mouth of the duct is aimed pretty much, it's down at an angle a little bit, which is fine. And you'll see why in here in a second, but it's aimed down, but it's aimed at the intake or the outlet of the main inlet here. So this is essentially a 6-inch circle here. It's the same surface area, cross-sectional surface area as a 6-inch circle going into 3-inch and then down to what is essentially 2 1/4 at the back of the duct. So airspeed from there to there is going to increase dramatically, which is good. So let's try left. Let's go the other way. All right, so there's straight. There's 1 1/4. So 1 1/4, you can see things get much tighter. You can actually see better than I can. However, we have space, so we're good there. Now, the reason this angle's down, which I realize now might be a little too far down, we might be able to angle this up just a tad, is so that the pipe, when it comes out of here, doesn't hit this frame rail. But it looks like I could actually come almost level out of here and try to reduce some bending to get to here. Sorry, this is all kind of tight, but looks like we have good clearance everywhere. It is tight at the damper fork up front, but again, it's not touching. So we're in good shape here. The reason there's heat tape all over this is because when we take this shield off, it's going to be unprotected from the rotor, but it will allow the rotor to radiate heat kind of into the open rather than have it reflected back by this dust shield. So this won't be here, but this is looking good. I think we have a usable part here. Just got to figure out, I think the brake line will be just fine. It's going to be resting on it at full lock. Again, we only go 180 degrees on track. That's the tightest turn we can find, and it's a left-hander at National Corvette Museum in Kentucky. So I think we got usable brake ducts here. Now, if the rack limiters fail, we're definitely going to crack them. But I think these going from the 6-inch down to the 3-inch to 2 1/4, I think that's going to be much better than these guys. That's the little aircraft fitting that we had on it before. And I know last video I kind of showed this, but just so you can get an idea of what we were dealing with. This was the old brake duct. So a lot of bends, a lot of tight bends and small diameter tubing. And then the other thing is, it goes into this area here, and let me turn my flashlight on. And you can see it is directed into the rotor, but there is a chance for air to escape out this gap. And I don't know what the airflow from underneath down here coming up through here is like, if it's creating a vacuum that might pull more of the air out this way. The new one over there definitely forces it, you know, right into this area here on the back side of this hat. So I think the new design will work much better as long as we get the rack limiters in, because otherwise we're going to smash the shit out of them. Okay, so the next step at this point is to take what I've learned on the car here, and we got to go home and make those changes in the CAD app. So I just need to angle that mouth up a little bit, maybe rotate that flange just a skosh, but I also want to put some fins in it to kind of help direct air and stiffen it. A few changes we'll go over at that time. The other thing is I have to make some changes to my printer to print the blended material that I plan to print the good ducts in, the final product. After that, we print them. So that's what we got to do now. So let's go back to the house and we'll work on the changes and start working on the printer. Okay, so as you can see behind me, we are back in my office in the house that I alluded to earlier that's been taking up all of my time. It's obviously not quite finished, but anyway. So this is where I've been working on these brake ducts, and this video has been a little all over the place because it's been hard to go through this development of these brake ducts. It's been one crazy process. But what I wanted to do is kind of take a step back now that everything's laid out in front of me here and kind of explain how I've gone from where I started to what I believe is the final product now. So I'm going to go through that and just kind of give you a quick rundown to kind of organize everything that's been kind of just thrown all over these videos in the last, 2 videos, so video and a half. So the first thing I did to make this all happen was, first of all, I had to have the idea, right? We have these brake ducts on our car that are constantly on our way, falling apart, kind of junk. So we needed a better option, right? So we got the idea. Now, what do we do about it? Well, I have these 3D printers right here that I'll show you in a minute. And I'm thinking, okay, well, is there a filament out there that can meet the demands of what we're trying to do with this car? Turns out there's quite a few. So they're close to the rotor might be an issue. So there's still going to be some development to do after this is all made and on the car, but that's what the test day is for. So we have the idea and we have the ability to make it. So now what I got to do is figure out how do I make it work. So I have an app called Polycam that I alluded to earlier. So what I did is I take a scan of the wheel, knuckle, rotor, caliper, and drive shaft assembly amongst the wheel bearing and hub and stuff. But I take a 3D scan of that assembly and it looks something like this. So when I get this assembly, then what I can do is I can put it into my 3D CAD app called Shapr. So Shapr will take that, I believe it's called a point layer, but it takes the shape, the 3D scan shape, which is pretty close to actual. It puts it in the app, and then what I can start doing is modeling around it. So I'm going to show you that here. So these are what I believe are the finished product. So we've got the right front here and then the left front right here. So you can see the right front has a 45-degree bend in it, 50-degree bend towards the center of the vehicle. That is because our intercooler piping hangs out right where the mouth of it would be, so we needed to come around the intercooler piping, but I can show you that later. So as far as the vehicle goes, I have the scan right here. And as you can see, the purple is all the drive shaft knuckle tire. So this was taken by a photogrammetry app called Polycam, which it did a fantastic job. There's a little bit of deviation, but I was able to skew the object to make it round. It was kind of ovaled where, you know, it was a little bit taller and not quite as wide as it was supposed to be, but it was very, very close. It did a great job of capturing the cavity down here in the rotor hat. Now what I was able to do from there is I took, let's get rid of these guys here, rid of the ducts, and then I was able to make these points, well, these polygons, I guess. So I made one here, 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 and these are all just constraints. And then what I did, so I can actually show you, it's a little bit cumbersome to do this. You select them all, and then you loft it, and it gives you your general shape. And you can move these points to kind of twist and skew the shape and make things more severe or less severe, whatever it is you want to do. So then what you do, actually that's kind of no good there. Let's loft that again. So we loft it, and we select the layer and we shell it. We tell it we want it to be 3 millimeters thick. It says okay. We click here, it says 3 millimeters, hit 0. And as you can see, you have a pipe. So we can see all the way up in the end. So we do that at the other end as well. And then we start looking at points where, you know, the brake line, the factory brake line mounted here, and this car did not have ABS, but this point here and this point up here were also points where you could drill for a 6x1 bolt. So I went ahead and drilled that and tapped it, and we have 4 mounting points now. There's a long stretch here where there's no mounting points, and I'm hoping it's strong enough. That's why the live data prototype is going to be so important. But after we built all these brackets and everything, we can go ahead and delete this shape, and we can turn off our loft layers. And then we can put our right front duct back. As you can see, we'll start here. I put, let's get rid of the vehicle for now. So I put a bead on it. So there is a bead rolled for the duct, and that is about a millimeter bigger than the internal diameter of the duct. So that holds quite nicely, and then just put a band clamp right here. This area here is for the caliper piston to be relieved. So that way when the outer pad wears, the piston will move towards this thing. And that should give me 3 millimeters of clearance when the outer pad is metal on metal. So we should be good for clearance here. This area here is for the brake caliper banjo bolt. I just found that tonight, and we'll go over that in a minute. We have the upper mounting bracket with a 4 mil thick rib down the center of it to strengthen that area. That mounts to where the factory brake line went. And then we have the outlet that kind of looks like a weird fish. This thing kind of looks like an eel. It's got these 2 bolt holes here and access a 17 mil diameter, 16 mil diameter hole for the socket to go through. And then the mounting points are 4 mils thick. So these will get covered up with some tape. I'll show you here in a minute, but I don't want them to be too inaccessible, just as in case we need to get these off during the race for some reason. So we'll be able to just poke a hole through the tape and then tape back over it. But there you go, rounded all the edges, made everything nice and, is laminar the word? We'll just use rounded. Made everything nice and rounded. I did not round the back of this because it's where 2 pieces will join. Then what I did is I just sliced all these things with just, I put just a square through it and then extruded the square 0.1. And what that does is actually divides these 2 pieces at all of these points. here, here, and then I just take one of the pieces and make it 0.1 millimeters taller, and that makes it a nice smooth shape again. So anyway, there is our right front. Again, that one turns because the intercooler pipe is in the way down here. And then our left front is more straightforward and just shoots right to the front of the car. So this one, kind of the same deal. It's a little bit different shape in this area because it kind of comes out and goes forward rather than coming straight down and turning. So there's less of a relief for the brake caliper piston and the banjo bolt there. But everything else from this point rearward is exactly the same carryover from the right side. So it mounts up the same and everything. It just shoots straight forward to the bumper, whereas the other side kind of has to go around some other piping and then go up to the bumper. So now that we have this designed, what I'm going to do is go through the prototypes that I have right here that I built. You can kind of see them. So let's take a look at those, and then I'll kind of explain kind of the development process through the CAD that I just showed you, because these are all a different step in the CAD program, but they're like a design it, put it on the car, check it out. Okay, that didn't work. Design another one, put it on the car, check it out. And it's just been kind of development stages to get to what I just showed you. So let's take a look at these. So bear with me because my lighting in this room is kind of poor still. I need to get some lamps and everything, but this was V1, the first one I printed. It was just out of some PLA I had laying around. PLA is polylactic acid. So that's just some stuff I had laying around. As you can see, there's marks all over it. So those two areas right there contacted the drive shaft, so that was no good. Then we needed an indent for the brake line, and just this thing did not work at all. So, but it was good. This was a good important step. Another thing you see is a 3-inch inlet, which is what we were trying to get because our old brake lines were 2s, obviously. But then it got choked way down right here, way down right here. Like I can get my hand all the way around that. And then it opened way back up. So the mounting idea has been the same. This one did have an extra bolt hole that we don't need, but the mounting idea has been the same. However, this thing was just not a great candidate, but it was important. It was one of the coolest things I ever printed, so I'm keeping it as a little trophy. But then we move on to the next one. So you can see the general shape is the same, kind of follows the same route. However, the outlet mouth is smaller because what I did on this one is I made sure that it progressively, as you cross-section this thing, it progressively gets smaller at each of those loft surfaces I showed you on that computer. Each of those lofts is 200 square millimeters smaller, from 4,400 down to 1,600. So, and then I deleted the ones I didn't need, but regardless, the idea is that this goes smaller in a linear fashion all the way to here, so the airspeed will continue to increase. This will build some pressure. This is small, but nonetheless, this was a much better shape. You know, you can see we just have the 2 mounting points at the brake line there, and we have the 2 mounting points there. We skipped the 5th one that was right there. So this was a pretty good one. Some notes on this one too. The outlet needed leveled because on the car it aimed down at the ground. And then there's move outlet inboard and forward. So you'll see how that panned out on the next one. And then obviously I played around with some of the reflective tape right there that will cover these holes eventually. So then that model led to this one. This one got the rib. This one got an air intake, like it was supposed to be a stiffener, but it was kind of like, those are actually shaped like airplane wings, like an airfoil, to kind of help direct the air kind of up the pipe. I don't know that it was going to make much of a difference, and the pipe is strong enough to be band clamped, so I just went ahead and did away with it. It's just one more thing to get in the way and cause us issues. I did put 2 more down here that actually go fairly deep into the pipe. Again, I don't think they matter. Same mounting points. As you can see, this one got worked with a lot more. It's pretty dirty. Again, it has the rib. There are some notes on this one, but you can't really see it. So this is where I learned that the caliper piston was going to touch it as the pad wore. And then I also put the note on here that it needs turn 45 degrees on the passenger side. So the thing was that even though I have that note to turn this 45 degrees, this one was already being printed when this one was being fitted, because these take about 16 hours to print on my current settings. I have some changes coming from my printer that will make it faster. So this one, as you can see, we'll start from the front here, the inlet. There is no more airfoil in it. There is a bead. This one did not have a bead. Well, it did, but it's really, really small. So this one has an actual bead. From there, I noticed, this might be tough to do one-handed. So it says gap to the damper fork is increased on this one because on this guy, it touched right here and was way clear down here. And there's actually notes written on it, but it was wet, so they came off. So I increased the gap to the damper fork at this area, and I decreased the gap to the damper fork in the bottom area. So this actually, this cross-sectional surface area here got larger to carry more air into the next section. So yeah, clearance was up in this section. Right here, I have a note here that I had to rotate the space 10 degrees. I did not end up doing that actually, but I did add 5 more millimeters of clearance. As you could see on the shape, wake up. You can see this shape is now we'll call it an eggplant. Anyway, so that clearance is up right there. So then the other thing was there was 12 millimeters to the caliper piston. We actually needed 17. So this note here is saying that these bolt flanges, instead of being 3 millimeters like the rest of the pipe, are 4. And then I also did away with the fins right there. Then this was the feasibility prototype part 3. So this was very close. This is actually going to work for the driver's side. However, as you saw on the driver's side, I did increase this and I put in a relief for the banjo bolt. So these guys right here will get printed in sections. Each of these will be its own individual part on the printer. These will take 2 prints, and this is the printer that I use to do it. It's a Prusa i3 MK3S Plus. This thing is fantastic. It does a great job, and obviously there's disarray right now, and this feed tube is not correct, but it's working right now to feed from the filament dryer that helps keep my PLA from being total garbage. So this thing eventually will be inside an enclosure, and the reason I need it in an enclosure is because, like, PLA doesn't mind being cooled when it prints. The heat bed keeps it warm enough. PETG doesn't mind an enclosed enclosure, an enclosed area to be printed in rather, but this ASA and carbon fiber is what I'm gonna print my final ducts out of. So this is just an ASA plastic with a carbon fiber filament, like shaving impregnated in it basically. So that needs to be in a heated enclosure. So I'm building the IKEA LAC enclosure. I printed off all of the parts I need to make the enclosure itself. That will just sit on top and feed my filament nice and dry and warm right through the top of the enclosure, and will feed the printer, and the printer will print. I have an LED for it as well, but the printer will turn on. Anytime the printer's on, the LED will be on. That's about it. I also have an Ender down here. The Ender is great, but it's a $99 printer versus a $900 printer, and this thing does a fantastic job. So the next thing I gotta do is print these parts I just showed you, because I need to test fit those to the car and make sure that everything is perfect on them, because this next step after that is to get the printer in the enclosure, change the nozzles, change a couple settings on Prusa Slicer, which is the software that makes the 3D print path, and then get the parts printed. So what I'm gonna do is show you what I set up on Prusa Slicer. That way I can turn my 3D model into a print path that the printer then takes filament and makes a part out of a string, basically. So let's look at that. And if you hear huffing, puffing, and lip smacking, that is this guy right here. Hey, Dooley. Hey. Dooley. All right, anyway. So back to these guys. These parts here, I believe, are my final draft, right? These are what I think are gonna fit on the car, but I wanna print them out of cheap material one more time just to be sure and make sure there's no snafus and everything lines up at least well enough to get us through the season where I can make the changes I need to for next year. So I take these parts and individually I export them into Prusa Slicer, and these look real psychedelic in this area right here. That is not your screen. That is actually what it looks like to me because it's showing the print path. So it's actually showing the tool path. So it gets a little weird on screen, but we have all the pieces here, right? We have the inlet with the bead. We have the next part with the brake duct reliefs and so on, right? And we got the part with the bracket right here, the outlet, and the other two pieces in between. So then what I do is I select the 0.2 millimeter quality up here in the right, and then I go into print settings and I change it back to 0.3 millimeter layer height just so I can get the quality, but I also want the 0.3 millimeter layer height. Another new thing is down here, Arachne. I haven't tried this yet. This is the first time I'm gonna try this. It's supposed to help with perimeters and make a faster and a higher quality print. And I turned on the support material and then limited it to a 25-degree overhang, which basically just kind of turns down the amount of support material because quite frankly, I'm about out of PLA. I have about 100, maybe 200 grams left, and this is gonna take 290 grams. So, or I'm sorry, it's gonna take 200 grams and I have 190 here, so it's gonna use. So I'm gonna come in at a photo finish here, but we're gonna give it a try and see what happens. Turn my infill way down just to give myself a little bit more margin. And what infill is, for anybody that doesn't know, is if you cut these apart, you'll see this yellow and red in here. That is your infill layers. So the red is what it's doing to like bridge the gaps without making a solid part, so you can turn that down and up. So I have it at 5%, which is probably plenty. So then what I do is I essentially export this called a G code. That's my print path. So I export that G code and I open up an app called Pronterface. And what Pronterface does is it allows me to, it takes away some features that you get with the Prusa, but what it allows me to do is I can reset the printer, connect to it, load a file. This is the most recent one, open. So what it's gonna do now is it's going to plot the tool path. Toolie. Bro. So what it's doing is it's plotting the tool path. I'm gonna go ahead and set my temperatures on the printer. So it's heating the extruder and the bed right now. And then what I'll do is when I'm ready, I'm gonna hit print and the printer should go. So given the fact that we're ready to go, off we go. So the printer's already, it warms up really fast. It's already just about at temp. So in a second here, you'll see it start going and it will do its bed level check. Let's use a magic eraser and wipe this off. Except for the fact that I screwed up. I need to switch the beds. Uh-oh. All right, got the smooth bed on there, so disaster averted. Break that off. So now, next thing to do, the printer's warmed up. I got the file loaded. We'll click print. Wait for it. Here we go. All right, so what the printer's gonna do now, it's gonna come in and do its bed leveling calibration, so it knows exactly where the bed is. This little sensor on the side there with the red light in it will tell it how far it is from the bed. So it checks 9 points to know exactly what the dimensions of the bed are in relation to the head's movement. And here we go. So it spits out a little bit of extra filament there. And it prints its perimeter. And in 14 hours and 51 minutes, we will have our hopefully last iteration right side brake duct. And that is where I'm going to end this video off. The next video is going to be this duct getting put together, put on the car, double checked. From there, hopefully, it will be assembling the IKEA enclosure for this thing, getting it in there so we can print the actual part out of the carbon fiber, ASA with carbon fiber, and then doing some other work on the car and just prepping for Mid-Ohio. So with that, I'm going to end it off. Thanks for tuning in, guys. I appreciate it, and we'll see you next time.